Recently, NASA released footage of an American football being thrown on the International Space Station. It's a really great video and it got me thinking this is a great opportunity to teach some physics. The ball is moving at the same speed and in the same direction relative to the ISS, and it's not changing. In good physics language, we would say that the ball is maintaining a steady velocity. An arrow showing this velocity being a vector can be expressed in any way the person doing the expressing wants. So just as I might decide to write 5, I can also write 2 plus 3 is 5. Or I could write minus 4 plus 9, which also means 5. Or even minus 3, minus 3, minus 3 plus 9 plus, in brackets, 2.5 times 2. They all end up meaning the same thing. Just as you can do this with normal numbers, you can do the same thing with vectors. If we imagine that the ball was moving diagonally relative to the ship, we could draw a vector for it, this red arrow. Since a vector is just like any other number, we can split that up into two components, one vertical and one horizontal. And this, if it's in meters per second, will tell us how far along in the vertical and horizontal the object will move in each second. This is essentially an application of Newton's first law of motion. An object in motion remains in motion with the same speed and same direction, or the same velocity essentially, unless acted upon by an unbalanced force. In the amazing series Cowboy Bebop, Spike finds himself floating or drifting through the vacuum of space. Nothing's going to change his velocity unless he's acted upon by an unbalanced force. He decides to pull out his gun, and by ejecting the bullet, pushing the bullet away from him, the bullet pushes back on him. He's able to alter his velocity, and in the end save the woman and live to fight another day. If we go back and watch one of these clips again in slow motion, we see a nice demonstration of the third law again. So Spike pushes on the ship and the ship pushes on him. Each of the forces will be equal in magnitude, but we also notice that Spike's acceleration under the force was different to the ship's, and these accelerations could be calculated using Newton's second law, which is F equals ma. Since the ship's mass was much larger, its acceleration was smaller. So it's a nice demonstration of all three laws happening at the same time here. A couple of years ago, I decided to record some students passing a ball to each other. Now this is happening inside of a gravitational field, that of Earth. And what you get is this parabolic curve. The reason for this is because Newton's first law in the vertical is not being applied, and that's because gravity is the unbalanced force. The displacement of the ball in each frame is represented by these green arrows, and as you can see, the ball moves the same distance in each of the frames, meaning that its horizontal velocity remains constant. However, in the vertical, because an unbalanced force is acting, the velocity starts off with a large positive value and then decreases, getting smaller and smaller and smaller until at the peak of the parabolic curve it is 0 in the vertical, and then it starts to increase in magnitude as it gets closer towards the ground. If we look at the velocity vectors in the horizontal and vertical components for the ball at each of these instances, we can start to think about what the ball's actual velocity would have been at each of these instances. So that would be summing the green and red arrows, which is represented by the yellow arrow. So I hope you found this video useful. It's just a summary of some vector information and things like Newton's three laws. Thanks for watching. If you liked it, please comment, like and subscribe.